Okay, we'll have a look at the 2016 basic skills test, and we'll just go through it to just make sure that some concepts have been locked in. So first one is draw the deflected shape. So I've drawn it out. So I've got the model here. So that's obviously the pin. This one here would represent a roller, not allowing movement in these two directions, but allowing movement in the horizontal direction. And then we're sticking a load down there. So as I stick the load down, you can see how it deforms. Okay, so I'll draw that deformed shape here. So that would be going down like that. And then of course I'll note that that's the tension side, and around here that's also the tension side. Now back to the model. If I remove that and then I stuck the load down there, you can see that goes up. Therefore the reaction must be going down. So that fits out of place. So the reaction must be going in the downward direction. So we could calculate the downward direction. We could calculate that reaction, and that reaction would be going downwards. And then we could calculate that one to be 5 kilonewtons. So that would be calculated maybe by just taking moments around that point. 20 times that distance would be equal to the reaction multiplied by that distance there. Now with the other one, we've got 20 going downwards, as we've seen there. So 20 going downwards. Now if this one had been removed, that would have gone down. Therefore that one, the reaction must be going upwards to make sure that this point here goes back to its original position. So if that had been there to stop movement in the up or down direction, we could therefore conclude that the reaction was going in the upward direction. So I'll put an upward direction there, and in terms of the loads, if that's 5, this is going to be 25. So that you've got equilibrium, or alternatively take moments about that point and you'll get that reaction there at B multiplied by that distance must be equal to the 20 multiplied by that distance. So the next bit is draw the shear force diagram. Use 1 grid is equal to 10 kilonewtons. So we've got 5 going upwards there. So the convention for plotting the shear force diagrams, as we've discussed in class, is just to follow the direction of the actions and to move from left to right. It's just like drawing a picture, or it's just a convention basically. And the convention to follow is moving from left to right. So if each one there is going to be equal to if each one there is going to be equal to 1 square, sorry, I'm having trouble focusing on the page. If each one is going to be 1 square, then the shear force diagram would look something like that, because that would represent the 5, and then it will go up by 25, so 5, 10, 20, and then it would go along down there and then back down to 0. So that distance there is going to be equal to the 20. That distance from here to here is going to be the 25, which would be acting upwards. So I'll just make that a bit clearer that the 25 is going upwards. So from there to there would be 25, and then you've got this 5 which is going down there. Alright, so that would be drawing the shear force diagram. Determine the shear force acting 2 meters to the right of A. So that would be A, so we would be effectively taking a cut somewhere about there. So to the left hand side of the cut, if we make a cut there, that force is downwards. So on that one there would need to be 5 in the upward direction. So that 5 would be in the upward, that 5 would be in the upward direction, and then on the other side of the cut it would be like that. So the shear force, I've determined the shear force to the right of A. Is it up, down? So by equilibrium, if I took I just drew that there, so that's going downwards. So on either side of the cut, the shear force would be downwards. Sorry, the shear force would be upwards, which I've drawn there. And the value of that shear force would be 5 kilonewtons, and on the other side of the cut it would be in that direction there. So shear force diagram, as I said, is artificial, it's just a sketch. What you're really trying to do is get to the free body diagrams, or make sure, or demonstrate you understand the free body diagrams, which is which way these arrows go. So 2 meters away from A, and then we've got 5 kilonewtons, and then it's going to be up down, as we've seen there. So draw the bending moment diagram for this loaded cantilever beam. Use the grid is equal to 10, 1 square is equal to 10. So that's 20, and that distance there is 1. So the bending moment at any point is going to be 20 times 1, so it's going to be 20. So right here, right at the tip, the bending moment would be 0. So right at the end here and there, the bending moment would be 0 because there's no curvature in the member at the end. We can see here the convention would be plot bending moment on the tension side. So you can see that this side here has all gone into tension. So we would be assuming that the bending moment would be plotted above the line here. So 20 times 1, and each square is 10. So 10, 20 would take me up there. And it would be a straight line down there. And then it would be a straight line going up there. And then we would show the bending moment like that. So I'm not really bothered whether it's positive or negative, as I've mentioned. I'm just interested whether it's above the line, which would be hogging, or whether it's going to be below the line, which would be sagging. So circle which of the following describes the bending moment at B. So we've got the bending moment here at B. Okay. So you obviously can have 2 free body diagrams. So at B, well, firstly, let's get the arrows. So I would draw that, and then I would draw that, and then you've got 2 choices. You can either put both arrowheads here or both arrowheads on that side here. Maybe I'll draw it like there. So these would actually be the bending moments. So if we had a free body diagram of BC, the free body diagram of BC would look like that in terms of the arrows, and if we had a free body diagram of AB, it would look like that. And what we say is we put the arrowheads on the side of the bending moment diagram. So if you knew the tension side, which would be the side of the bending moment, then that would tell you which way the arrow would go. So when we look at this one here, circle which of the following describes the moment at B. B is a hogging moment, and what would describe the bending moment at B would be that case there. So that would be what would describe the bending moment there. So let's just draw a free body diagram. So we'll take a free body diagram of the bit out from B to C, so the arrow would be like that. We've got our 20 kilonewtons going downwards, so there would be a shear of 20 kilonewtons going upwards there. And then if we took moments about that point, that one would be going in the clockwise direction, so this needs to go in the anti-clockwise direction, and the value of that arrow there would be 20 kilonewton meters, and then that value there would be your 20 kilonewton meters in terms of hogging. So these arrows will later on, when we get to the slope deflection method, we will be calculating the magnitudes of these directions from the free body diagram. Right, so let's move on. So next part of the test is this case here. Draw the expected deflected shape for the loaded cantilever beam shown. So this time here, we would have this bit here. So this permits rotation. I'll take that off and I'll put it with something that doesn't permit the rotation. And then we've got this case here, and then this time the line is going upwards, which we can see there. So all of that would be the tension side, and let's put that even more up, and you can hopefully see, if this doesn't snap out when I exaggerate the deformations, that that the top part here goes into tension. So tension there, and then tension side there. So let's draw the deformed shape. So the deformed shape, that point there wouldn't move, that point there would be going upwards, that would be coming out at 90 degrees, and that would be going down and then going all the way up there. Maybe I should put show some curvature. So I need to show some curvature in that line there for the deformed shape. So that would be tension, that would be tension there, and then that would be tension there. Okay, on that side there. So hopefully with that deformed shape, you can see that there is tension on the top side. Now it says sketch the bending moment diagram. So the bending moment diagram, tension on the underside. Down here that would still be tension, so the bending moment diagram would look something like that, and then tension on the top side would go something like that. Okay, so that would be the shape of the bending moment diagram, and where the bending moment goes to 0, that would become your point of contraflexure. Okay, so that would be the point of contraflexure where the bending moment is 0. So let's have a look at the reaction. So here, if this end here had been that instead, and so I bend it up so you can see that rotating down, but now I'm going to turn that round so that it's back to the 0 position, or there's no rotation, which is what happens at the fixed end. So that would be the fixed end. So that rotation, to get it back to 90 degrees or coming straight out, which you can see there, I'm having to rotate this in an anti-clockwise direction. So when I draw my reaction would be like that. Okay, I'm going in that direction there, which you can see from the direction that I've had to rotate this in order to maintain it back at 90 degrees. So if we forgot about that, let's just make a fold on the paper so that like a hair's breadth away from the end. Okay, so I've just made a fold there, and then I'll do my thing with the arrow again. So we should be happy with the direction, and then that would be the bending moment. So that would be the bending moment just a hair's breadth away from the edge. So if I did a free body diagram, a hair's breadth away from A, so a free body diagram, a hair's breadth away from A, hopefully you could see that that would be the direction of the arrowhead. Okay, so when it says circle which of these shows the bending moment, yeah, that one there would be the answer. And you can see that this is in the same direction as that arrow. Okay, now for the propped cantilever, a point moment is applied at the end, is restrained at the end. Draw the expected deflected line. Show locations where you expect the tension to occur, and then write the T at the side. So this time I'll set the model up. Like this. Okay. Emily, I'm recording, okay? You don't come back. Alright? So, now, let's have a look at this one here, where it says that we are this one here. So here I've got the fixed end, which I've got there, and then I've got the same thing coming off here, and then my thing here. So this time it says right at the end, so before maybe we could be saying we're putting a load on in that direction or in that direction, but this time we're putting a rotation. So the rotation is in the clockwise direction. So you take this and then you would rotate. So just get my two fingers, and then I would just twist my fingers round, and you can probably see that as I'm twisting or causing that to rotate round, so that would have a slope. You could probably see that it has to rise. Okay. So a rotation at the end, or a moment at the end, that point doesn't stay fixed in space. So it's not the same as having a roller there, okay, or having another pin. When you rotate it, you would be putting a twist. You would be causing a rotation at the end, and the rotation, if we can fix it like that, you can see that there would be a slope. So originally it was like that, and now it's like that, which is the direction of the moment. So the moment is in the anti-clockwise direction, is in the clockwise direction, and you can see that that has now moved to a clockwise. That line used to be there, and it's now moved clockwise. So at the end of here, you would expect this to have moved up. So as we can see there, just drawing that one going round like there, and again you could see that's going to be tension, that's going to be tension, and as we've seen there, that one would be in tension too. So what we could do is we could replace that end there with this thing here, which permits the rotation. So I'm going to be twisting it round, and you can see that rotates. So that one needs to be going up like that, and you can see the top face going into tension just there as that is going up there. Okay. So that one would be in tension. Now the next bit is sketch the bending moment diagram. So the bending moment diagram, tension is on the underside, so that would be hugging there. This bit here would be up here. Okay. And if you just bear with me for a second. So as you move from this side to here, from there to there, we can see there's nothing happening from here to here. So whatever the bending moment moving from left to right is, that pretty much needs to be constant. So we'll be drawing constant bending moment. which is consistent. So that since there's no change of bending moment, since it's constant, there's no shear. Yeah. So which I'm moving from here to here, there's no vertical force there like you would have with a cantilever. So you'd expect the bending moment to be constant. And then from going from here to here, there's nothing happening between these two. We know that that side going to be the tension side, and so we would draw the bending moment diagram like that. Okay, so that would be the sketch of the bending moment diagram. Now, if we wanted to draw the arrow, so obviously so if we did a small cut just to the right of there, and I'll fold the paper so that we could see the small cut just to the right. So small cut just to the right, and then that would imply that that bending moment needs an arrowhead there. And you can see that that is the same as that. Yep. So that's an external one, which has caused this bending moment, which has caused the bending moment when you do a small cut away from it, and it acts in that direction there. And similarly, if we could do something like there, right there, and then if you looked at the reaction solution, you would see that when this end here, as we said, so I'm applying a moment going up there, so that needs to be in that direction, which would be in the clockwise direction, and so the reaction at the end there would be in the clockwise. So this one here would be the reaction moment, and then this would be the bending moment, which you would find through a fictitious cut just to the left of the support there, and you can see they're both acting in the same direction. Okay, so let's move on. So cantilever beams. So if I did a cantilever beam here, I think could be like that. So we could have a cantilever beam like there. So again, zero rotation here at the ends here. So that's the cantilever, and me putting on things on both sides. That's almost exactly the same length, and what we'd do there is we would have that, and then I would need my roller. So this time I use this as the roller here. Okay. So if I pushed that one down there without it snapping out, so hopefully you can see this, and then if I'll do it very small. So here two forces going upwards at the end of this one here, and this one here, one force twice that size going down there because it's the same beam. Okay, so if that was say 10 kilonewtons, which applied through the pencil, then these would be 5 kilonewtons there. And you could probably see that the deformed shape is exactly the same. Okay. So what does that tell us? So the cantilever, which we see there, we've got P there. So two cantilevers emerge from a common wall support. Draw the expected center lines. So you would expect the center line to go like that for the deformed shape, going in at 90 degrees, and then this one here, the mirror image, going up like there. Indicate where you would expect the beam deformations would have the smallest, would have the maximum radius of curvature, or the radius of curvature to be the maximum. So you would expect the maximum to be right at the end, or in fact it's infinity, because the bending moment at the ends of this are 0. So when we've got our cantilever, you should all be quite happy that the bending moment there is 0, and I've just shown that's going to be the same shape. So right here, that's where the bending moment is going to be biggest. And remember, bending moment is proportional to curvature. So if I can keep on moving this up, and it will clearly snap there, which is what a bending moment diagram should show, and it's not going to snap here. And similarly, when I pull this down here, if it was going to snap, it would be snapping at that point. So bending moment is proportional to curvature and inversely proportional to the radius of curvature. Now, next bit here is sketch the shear force diagram with our P. So the P is going upwards. So so we can see that's the baseline. So because the P is going upwards, let's just say it's going to go like that, and then it's going to go like that. So that would be the shear force diagram. And then let's plot the bending moment. Let's plot the shear force diagram here, and the shear force diagram of that side would be like that, and then going upwards there, which would be implying that the reaction there is downwards P, and the reaction here, so that's upwards, it would also be downwards. Okay. So let's move on, and it says sketch the bending moment diagram. So we can see that these are not symmetrical, but when we draw the bending moment would be plotted on the tension side. So that would be the tension side there, and when we put the force down there, that would be the tension side there. So the bending moment diagram would look something like that for that first one, and then the bending moment diagram for the second cantilever would be like that one there. Okay, so you can see that the shear force diagram is artificial, as we've said. It's just a plot or a sketch that's useful to help you interpret free body diagrams, and it's artificial, and you can see that it's not symmetrical in this case here. But the bending moment diagram is symmetrical, and if you remember that bit of tracing paper that I had, the bending moment is plotted on the tension side, so it should be symmetrical. You're plotting the bending moment on the tension side. So the next bit is draw curved arrows for each of the beams showing the direction of the reaction moments at ends A and B. So this would be the reaction moment at the end there, and that would be in that direction there, and that would be the reaction moment there. So if I drew this one out here with the P going upwards, and you've got that there, the reaction moment would want to go upwards. So let's replace this one here. Let's replace this one with this one here, and we can see, put the force up, and then that one would have to be rotated around in that direction, okay, which would be in the clockwise direction. So this one here, the reaction moment, which I'll draw there, would need to be in that direction there, okay. And on the other side, which maybe I'll show here. No, that's getting too hard to show it there. I'll tell you what, I'll just scrub that one out, and then I'll show that one there. So you've got your P going upwards, and then the reaction moment must be in that direction. So those are the reaction moments. So these are the reaction moments. Next question is it a sagging or a hogging bending moment diagram? So it's sagging, so if at least for beams, if it's above the line, it's called hogging, and if it's below the line, it's called sagging. Okay. Draw curved arrows to indicate the internal bending moment at C in the case of a simply supported beam, with the point load at the span. So this is what we are contrasting it with, the simply supported beam. So we've got that case there with the reaction going downwards, which you can see there. So we've got this with the reaction going downwards, and if we drew the bending moment diagram of this one here, it would look something like that. And then if I wanted to say plot span that one, that's the free body diagram from here to here, again put that, and then it will go on that side, this tension side, or the side of the bending moment, and on the opposite side it would be the same. So you can see this is going, the reaction moment is going in the clockwise direction, and the bending moment for the simply supported beam, as you would expect, is also going on the same in the same direction. So sketch the shear force and bending moment diagrams for the simply supported beam, and observe whether these are different to the earlier case. So the shear force diagram, go up, down, across, and then up again, as we've seen many times. And then the bending moment diagram being symmetrical and going like that. And if we contrast it to what we could see from the two cantilevers, we can see that the shear force diagram is the same, and we can also see that the bending moment diagram is the same. So now let's move on to the multi-span beam. So draw the expected deflected shape center line for this loaded cantilever. Show the locations where you would expect tension to occur by writing T. So before we start, so in terms of deflection, that point will not be moving up or down, that point won't be moving up and down, that point won't be moving up and down, and then this one here, you would expect that to be going down like there. All right. So we've got some known points which I'll put with a cross, and let's see if we can draw a smooth spline between those lines. So I'll try and draw a spline between those lines, so we can see that one go up, then that would need to go down, and then that would need to go like there. So we would expect it to be something like that. So now if this one disappeared, if that point disappeared, then that would probably go further down, and that would then go up, as we can see. So we could probably conclude that the reaction at C needs to be going upwards. Now if that one disappeared, then it would probably trace that path. So if that B support disappeared, it will probably trace that path, and that tells you that the reaction at B must be downwards. So I'll draw a downward reaction there. And then the final one, if that A disappeared, we would trace that, and that would just continue to go down like there. So the reaction at A, you could conclude, must be going upwards. So we got upwards, downwards, upwards for the reaction force. So show this in the shear force diagram. So I've sort of indicated the sizes of the arrows here. So this one, let's say that one goes up by 1 square. So along there, and then down there, that is down. So that would be on the shear force diagram plot. Then we'll move up here. That one's going to be bigger. So that one's going to go all the way up here, for example, and then move down there, and then that would be equal to that. So that's not really nicely to scale. So let me just try and alter that. So I'll probably start from there and then go like that. Maybe start that from there, then go down. So that is the same as that distance there. Okay, so that would be the shear force diagram. Then let's move over. Let's draw the draw the bending moment diagram. So the bending moment diagram, you would expect that's the extreme pin. So you would expect the bending moment there to be 0. Here you would also expect the bending moment to be 0. Down here you would say that has to be the tension side. So that would have to be the tension side, and then that would have to be the tension side there. So going from here to here, it would have to increase because it's a cantilever. So if you imagined, we've got the force downwards, and I'll just cover that with cover that so that doesn't get in the way. As you move from right to left with that force going down, you can see the curvature there. So it doesn't really matter what the boundary condition is. It's linear as you move along the cantilever, with the tension side being here. So we would draw something like that, okay, for that portion of the bending moment diagram. Equally, we know that that one is going to be 0 in terms of the bending moment. We saw in the earlier plot that tension is on the underside, so the direction of the reaction must be going upwards. So if you're not sure, you could repeat the same thing. Let's just move it around here, and then so let's forget whatever that is, and we've got the reaction going up. So you can see the bottom bit's going to be in tension, and that's going to be increasing linearly. And so there's nothing else there, so we would expect maybe something like that for the bending moment diagram. And then there's nothing between B and C, there's no lateral force there, so just join the dots. So we've got the bending moment plot, bending moment, so we would expect the bending moment to look something like that. And if we did a free body diagram of CD, so I would draw CD going out there with that force going down there, then I would maybe imagine that one going there. So that would be my free body diagram of CD. So that is the bending moment, which we'll be calculating in the next section of the course, and then that one would be showing the direction of the bending moment with the arrowhead on the side, on the tension side. Okay. Equally, if you wanted to draw a free body diagram of BC, so let's go there for BC, which would be the second, which would be the middle span. I would expect that to be the direction there, and then I would expect that to be the direction there, but maybe a bit smaller. So that would be the bending moment there, and then that would be the bending moment there. Okay. And I might just want to just label it up like that. Okay, and then the last bit. Well, let me see first if I can get that one in. Not sure I can. All right. So that one there, this one here, one space along here. Okay, so I'll have that there as, and with a shorter piece. So that, let's keep these down, okay. So put my load down there, as you can see that that wheel has spun has spun in that direction there. So tension side, you can see that is the tension side, and the tension side continues along there. Point of contraflecture is probably there. Underneath here, so here there would be hogging because the bending moment would be plotted on the tension side. That would be the point of contraflecture. Under here you can see that this thing here has gone into sagging. So not sure if that's the compass there. Oops. Going down like that. So if you looked in here, you might be able to see that that compass shows that that side has gone into sagging or underneath, and clearly on that side it's gone into hogging, okay, with the tension being on that side here and the tension being on that side here. And then here, zero bending moment. So neither sagging nor hogging. In terms of the direction of the reaction, if I got rid of that and then I stuck my load there, you can see, whoops, you can see which way it went between those 2 points, and then that would deduce for you that the reaction needs to be in that direction there, and then put that there. So I don't know how helpful these beams are, but you're welcome to take a set if you wanted to, and you're welcome to use it during the exam if it was helpful. Now this one here, I push this down, you can see that's going up, so that reaction must be going downwards as we deduced earlier on. And then this one here, if that one is lost, that goes down, that needs to go up, so that must be upwards. And the final thing I wanted to show was if these are the same force. Oops. So just forget about that. Just forget about that, what happens on that side there. If you put the same force at the end there, we can see they're exactly the same. Okay. So when you move in from this side here, if that was 10, then the bending moment would be 10 times the distance you are away from it. So in this case here, even though this is statically indeterminate, if you knew the force there, you would know the bending moment there, and the same way you know the force here, you would know the bending moment there. So both would be the same. And then the last bit is the point load at D has been replaced by a moment. So instead of that, we've got a moment. So this is now straight, and the moment is going in the clockwise direction. So that's going in the clockwise direction. So you want that to bend around, okay? Because the moment, it's either a clockwise moment or a clockwise rotation that's been applied. So if I twist the end there, you can see that that end has moved downwards. Okay, that end has moved downwards. Okay, when I twist that one there. So the change to this diagram here, that would be the same, and that would also be the same. And then what you've got up here is that you would have a constant bending moment. So if I made a cut, say here, if I just made a cut there, you would get one moment on that side and one moment on the other side there, which you can see, and that is in the same direction as that. Yep. So that one on the left side of the cut is in the same direction as that one there. So let's get rid of the cut. So when I draw the bending moment diagram, it would be like that. And then it would go like that. And then it would go like that. Okay. And in terms of the deformed shape, we've made it rotate in that direction, so the end is hanging out like that. So you would expect something like that to be the deformed shape, and then everything else you can reason out as before. So if I made a cut there and just pretended I wanted the free body diagram between those 2 points, so the cut is just to the left of B, then if I drew my arrows there, you would see it's that and that have to be the same, which you would sort of expect. Okay, so I'll get rid of that. So this is the class test that they would have sat back in 2016, right at the end of this section of the course. So you've also got the class tests from 2000 and you've also got the class tests from 2017, 18, 19, 20, and you've also got the past exam papers. So just go through them, solutions on the Dropbox, and anything else that you need to know, just let me know through Piazza or through an email.